We moved from deterministic models to modeling under uncertainty, and we started by introducing the 4 basic probability laws, the first of which is that the probability of any event happening is a number between 0 and 1, where 1 is ultimate certainty, it's going to happen, where 0 is it will never happen. The second law is that if A and B are mutually exclusive events, then the probability of event A or event B happening is equal to the sum of each of the probabilities. Think of rolling a die, and I want to find the probability of rolling either a 2 or a 3. That's going to be equal to the probability that I can roll a 2 plus the probability that I can roll a 3. 1/6 plus 1/6 equals 1/3. Third law, if A and B are any 2 events, then the probability of event A happening, given that B has already happened, is equal to the probability that both events happen divided by the probability that B happens. Now, the way that I typically see this is in this form that I'm boxing. And this is simply saying the probability that both A and B happen is the probability that A happened given B times the probability that B happens. You'll use this quite a bit when you come up with this. The conditional probabilities are very powerful. And we use this actually to test for independence. So the fourth law is if A and B are independent events, then the probability of A given B is equal to the probability of A. We then moved on to random variables in functions. We looked at the linear function, y equals ax plus b, where y and x are random variables. And we found how to get the expectation and the variance of the new random variable y. Then we went into sum of random variables, where if I have random variable x and y, and I want to have a linear combination of those, a times x plus b times y, that gives me a new random variable z. And we showed how to find the expected value and the variance of that new random variable z. We introduced the concepts of a covariance and the correlation, and we'll define those precisely in just a minute. Then we moved into characterizing a distribution, because in supply chain you're going to have a lot of data. So if I have a bunch of data on demand or transit time, it all won't be one number, right? I'm going to have a distribution. How do I characterize that distribution? There's 2 main ways. The first, central tendency, and we looked at 3 metrics: the mode, the median, and the mean. And then the next is the dispersion or the spread, and we looked at the range, the min and the max values, the interquartiles, which is just the 75th percent value minus the 25th. We looked at the variance and standard deviation, which is just the square root of the variance. And then the coefficient of variation. You'll use this a lot. The CV is very widely used because it normalizes the sense of variability. So we'll always look at the coefficient of variation to be able to compare different distributions. So you should be very comfortable with these 2 formulas. That is that the expectation of random variable x, so we'll call this x bar or mu, and that's equal to the sum of the individual probabilities of each event times the value of each event. And the variance is simply going to be the sum of the probabilities times the value of each event, xi, minus the mean squared. So it's capturing the spread around the mean. We then moved into identifying discrete distributions, and we focused on 2. There are many other ones, but we really focused on 2. One is the discrete uniform, where you have an equal probability of integers between 2 variables, a minimum and b the maximum. And we said the probability of each is 1 over n, where n is equal to the b maximum value minus the min plus 1, because you have to make sure you count them all. The Poisson is another very powerful function, a discrete function, and we'll use this a lot when we talk about slow-moving inventory or arrival rates for different models. And so it's very important because it has some really great properties. 1, it can't take a negative value. 2, it works well with low numbers. And 3, as I increase the lambda, as it gets larger, then it starts approximating that normal distribution that we talked about, that bell distribution, bell-shaped. And so as lambda gets bigger, then it starts approximating that normal distribution, which is kind of interesting. Also, while the output of the Poisson are all integers, the lambda, which is the parameter, does not need to be integer I can have a lambda of a 0.75, for example, because that's just the average or the variance. We then moved into continuous distributions, and we focused on three. First was a uniform distribution, and it's just like the discrete uniform distribution. You have a minimum and a maximum value, and here I have the PDF, 1 over b minus a. And then I introduced the triangle distribution. Now, the triangle distribution is not as widely used in supply chains. I like to use it for estimating. I think it's a very powerful back-of-the-envelope distribution because it lets you understand a minimum, a maximum, and a likely value. You can see that these two distributions are very similar. They both have a min and a max. The only difference is the triangle distribution allows you to model non-symmetric distributions. Because as we saw when we look at the normal distribution, which we'll look at next, it's very symmetric. And a lot of things in life are not. So this is one quick way to model something that's an asymmetric distribution, and also you can model it so that it won't have any negative values. So it's pretty powerful, and I recommend that you keep this in your back pocket. And we finished up with a normal distribution. You will use this a lot. This is widely used throughout supply chain and for a bunch of different reasons. It's very common, and it's just widely used, especially when we talk to inventory. And so while using the normal distribution, you'll also be using the standard unit normal, where the distribution here, it's just where I'm normally distributed with a mean of 0 and a standard deviation of 1. And so you need to be able to transform back and forth from your distribution into the standard unit normal, because you use this to get the z-score, or what I'll call later the k value, to understand how much more above the mean I want to set my value. So these are the initial steps we did for modeling uncertainty. We looked at distributions, both discrete and continuous, and reviewed basic probability laws.